there's one little trick that matrix multiplication lets us do that will turn out to be of great use, mostly for saving time. So I don't know about you, but I have gotten extremely tired of writing down giant systems of equations like this. But now that we have some extra tricks involving matrices, let's see if we can come up with something better. So if you look at this left-hand side, right, every row is just the sum from k equals 1 to n. So it says every row on the left-hand side, every row is a sum with n terms, and each term is a something k xk. And what goes here in this first index depends on what row you're on. Usually we use I to indicate what row number we're on, so let's write I right here. And on the right hand side is just b sub the row number, but that's I. Okay, but this looks like it's a matrix product. In fact, it is a matrix product, except the x's, right, they have it doesn't look like these x's came from a matrix because there's only a row number, only a row index on this x. But if we pretend that there's also a column index, it just happens to always be 1, then all of the a's are coming from a matrix that's m by n, and all the x's are coming from a matrix that's n rows by 1 column. In other words, x is just a column vector, which makes sense because, right, that's how we were treating the x's. We were treating them all as a vector. So this is, and so what position in the matrix did this come from? Well, it came from row I and column 1, and there is only one column, right? So this thing on the left is actually a product of these two matrices at this position. So if we write out these matrices, so that the matrix with a's is A11 up to A1n, and then down to AM1 over to AMN, like this, times the column of all the x's, so x1 down to xn. And in this column matrix, we don't usually write the column index because there is only one column. So now you can verify that if you write out this matrix product, you do get exactly this left-hand side. So this matrix product gives us the vector that is the left-hand side of this system. So to write this entire system, all we need to do is say that this left-hand side is supposed to be equal to the right-hand side, but the right-hand side is also a column vector. It's a different size column vector, but it's still a column vector. So B1 down to Bm. Okay, so this linear system, we've actually expressed it using one matrix for all the coefficients, and then the column vectors. Now, of course, we still had to do a lot of writing to write out, this big matrix. But what we'll do in the future is we'll just say, instead of writing out all of these entries, we'll just say this is some matrix A, this is some vector x, and this right-hand side is some other vector b. So some people like to write their vectors using capital letters and some use lowercase. I think I usually use lowercase. So this matrix, capital A, is m by n, and that's all the coefficients. This vector x is n by 1, and since these sizes match, this matrix product is defined. And the resulting matrix is a column vector that's m by 1. So now, from now on, whenever we need to sort of express the idea of a linear system, we don't have to write all of this. Instead, we'll just write the m by n system ax equals b. And that's a great labor-saving device. So if nothing else, the matrix product is useful just because it saves us from having to do all of this writing. We'll see that the matrix product actually shows up in a lot of other situations. So, we'll get a lot from having the matrix product around. But if nothing else, this is a good thing.